Hello, I want to talk to you today about cyclotrimerization of alkynes, a really useful way to make substituted benzene rings, starting with 3 separate alkynes. And we're going to do a couple of examples, one in the forward direction, one retrosynthetically. We talked about the mechanism in class, so I'm not going to go through the mechanism. I just want to show you how we can use this reaction for a couple of examples. So what I've got on the board right now is just starting with this bicyclic imine. We can functionalize that with a nucleophilic alkyne, the Grignard, and then an electrophilic alkyne, the propargyl bromide, so that we add to the imine, and then the nitrogen nucleophile can add to the bromide electrophile, and we get this diine. And we can do some interesting chemistry with that if we add our cobalt catalyst and another alkyne. Right? So let's just take a look at a couple of examples of how we can functionalize this using our cyclotrimerization reaction. Right? So the first one is just going to be if we add KOH. KOH will enable us to deprotect the solid group on that alkyne, so we can remove that, just replace it with a hydrogen. Right? Then we can do our cyclotrimerization reaction. Right? So we'll add an alkyne with 2 TMS groups. Right? And then we can add our cobalt catalyst. Right? So here we have our 3 alkynes. Right? Those can come together. And this is a good predict the products problem. So if you want to pause the video now, you can predict what we're going to get for the product. We'll end up in this problem making a tetracycle. Right? So what is that going to look like? Right, and so those are our original rings, right? And then we're going to have that new 6-membered ring, right? If we count along here, 1, 2, 3, 4, 5, 6, we're going to join 1 and 6, right? So if that's 3, 2, 1, 4, 5, and 6, and so then the new benzene ring is going to be in that position, right? And we see that the new alkyne is going to be positioned out here. Right? So a very nice way to make that tetracyclic compound. We also can react this with a nitrile so that we can make a pyridine ring, not just a benzene ring. So if we react this with phenylnitrile, again, the same cobalt catalyst, right? We can do the same chemistry that we just did, but now we'll end up making a pyridine ring. So again, a very nice way to make either heteroaromatic or just benzene rings using the cyclotrimerization. Said we would do another example where we thought retrosynthetically. And so the most popular, probably most well-known example of using this reaction is in Volhart's estrone synthesis, right? The structure of estrone estrone's a steroid, so it has the standard steroid backbone. And then it has a phenol ring over here. And the first retrosynthetic disconnection was the following. Right, it was to say that we could get to that phenol from that di-TMS substituted benzene, right? And this is where we can think about using our cyclotrimerization chemistry, right? And the thing that we can think about is what happens if we don't try and make this ring using the cyclotrimerization chemistry. We make this ring, but not right now, all right? When we saw in class, we were able to do a cascade where we were able to do an electrocyclic ring opening after the cyclotrimerization and then a Diels-Alder reaction. So the way to think about this retrosynthetically is not to disconnect this ring first, it's to disconnect the central ring using a Diels-Alder reaction, right? So that's what we want to do first, is do the Diels-Alder disconnection. Right. So we can do that. So that gets us to that substrate, right? That substrate is going to be very reactive towards the Diels-Alder reaction. It's not going to be stable, something we're going to have to generate in situ. Where does that come from? That's going to come from our 4-pi electrocyclic reaction. Right, and so that's the substrate that we're going to end up making in the cyclotrimerization reaction. The rest of the molecule looks like that. And so again, this is our key substrate for the cyclotrimerization reaction. So if we imagine what this comes from, right, we're going to end up forming the other, actually let me cheat and I'll just erase, and we think about that resonance structure, right? Because if we do the retro cyclotrimerization, we can imagine that disconnection. And so then what does that look like for us? We end up with that alkyne, and then the other piece is a diene, right? So that would give us right, that diene, and then connected to the rest of the molecule. Right? So a beautiful cascade here where we do in the forward direction a cyclotrimerization, a 4-pi electrocyclic ring opening reaction, and then a Diels-Alder reaction. So just a beautiful example of reactions we've studied this semester to give us that steroid backbone, right? And it's an interesting problem to think about, how did Volhart end up making that substrate, right? So that's something that you may want to think about. There's some standard chemistry, right? You can think about this 5-membered ring and how you might functionalize that. The starting material that they started with for the 5-membered ring. Okay, so if we go backwards from here, they started with that cyclopentenone, right? So I'm pretty confident that you can come up with a synthesis of this in the 4 directions starting from here. So that's something that you may want to think about. And then the alkyne piece, they were able to start the alkyne piece with that alcohol, right? So think about how you could come up with a synthesis of this, starting with these two starting materials and whatever else you would want to come up with. And if you're curious about the answer, just let me know. You also could probably, without too much trouble, just Google Volhart's estrone synthesis, and you would find it. It's also in Classics in Total Synthesis by Nick Lau. So anyway, these are good examples of using the cyclotrimerization reaction, and I hope this helps as you think about your problem set and upcoming assignments.